Notion of uncertainty, and that is basically that we have a glass, we can't see it, we can't feel it, we know that there is a little water, we have no idea in what state they are. And so a disclaimer at the beginning of this lecture, this is absolutely not a complete introduction, or this is more a reminder of what I think most of you will have seen in courses, statistics courses. But it is a critical notion in AI. We use it a little bit next week for the machine learning part. But it is, as I said, it's such an important notion in AI that I wanted to give it at least a little bit of space in this course. There will be some exercises in the working group and in the exam. I'm not sure whether you can do a lot of it with your final assignment, so it will be mostly tested in the exam. But the purpose of this next 40 minutes is really is a reminder of this very important technology and methodology within AI. And this is a bit sort of trivial, but I think you can all understand that if you want to build something that's more complicated than a Wumpus agent or even a Schnapsen agent, where you can almost get away without probabilistic models. If you want to do something with a self-driving car and you want to do it a little bit systematic and formally grounded, then you need a good theory to deal with uncertainty. So the fact of not knowing everything and doing that in a rigorous mathematical way. And that's what probability theory has been for hundreds of years now, or more than 100 years. So you want you have an automatic taxi agent. The question is, will I reach my flight in time? And then I have some expectation of my environment. The roads are free or whatever. And it's an environment which is not fully observable. I can just sort of listen to the ANWB. Will there be jams on the road? Will there be traffic work on the streets and so forth? So you can imagine how difficult to be certain here that I really make it in time. And that's a typical thing that intelligent agents have to deal with. So we have obviously with Schnapsen a very, very simplified model, but even there we have the uncertainty as we can't observe what our opponent does. But in real, more realistic real life problems, this obviously becomes far more important even. So the sources are that the data is unreliable, your measurements are incomplete, you have someone telling you what the weather is going to be, or you have even bad measurements in the first place. You have someone who tells things that are different to what you would think, so there's some bias in the, it could be incomplete by broken sensors, or simply too much information that is available. And it can be imprecise. Sometimes it's necessarily imprecise, or it is simply you don't have good enough tools and so forth. So you can imagine there are millions and millions of different reasons for why we can't have always certain and complete information. And that means that we can, based on the uncertainty of what we know, we still need to make decisions that are somehow grounded and well understood. And first order logic or propositional logic, all these crisp logics, they are simply not sort of equipped for dealing with these kind of things. So this is an example from the book. If someone has a toothache, then the suggestion is that this person must have a cavity. Chances are high that this person has a cavity. But how do you model that? So toothache implies cavity? No, there are many different reasons for having toothache, even if you don't have a cavity. So this is wrong. You might have gum problems or whatever. And it's impossible to write down all the other options. So we have no means, we don't know all the other reasons for having toothache, and even if we had them, it would be completely impractical to write them down, all of them. So the other way around doesn't make any sense either, because there are many people with cavity who don't have toothache. So this wouldn't capture our knowledge either. So these kind of things are very, very difficult to model in the logical languages that we've looked into so far. So people in the last century have tried to come up with representation languages and formalisms that allow you to capture this in better ways. So the most known ones that still is very active research field is default reasoning. So we say that people have, we assume that people who have toothache also have cavity, unless we know that they might have other problems where the pain can come from. And this, assuming something until we know that it's not true, that's a very typical default reasoning. And you have basically your operators in which you specify that. But again, unfortunately, this is not very practical because this becomes computationally incredibly expensive and very difficult to deal with. And even then, the question is which assumptions are the ones that you would add as possible defaults and so forth. You could also apply a more sort of statistic approach or a quantitative approach and give some value to your rules. But then, first of all, where do these values come from? What do these values mean? And it becomes incredibly messy if you combine different facts. And there are approaches that work on these kind of rules with certainty factors. But they usually lack a mathematical foundation, and it's very difficult to understand whether they are really working as you intended them to work. So these were these certainty factor models that are easy to apply, easy to implement, and were very often used in early AI systems, but they lack a mathematical and theoretical basis, and are therefore sort of you don't really know what comes out. And that's different to the probability theory that most of you will have seen, I guess, which comes with a very strong theoretical foundation. And so that's what I want to spend a little bit of time on, to remind you on this theory, this important theory, and some of the important elements of it. So there are maybe an interesting philosophical background to that. There are different ways of looking at probability. One group that's sort of the frequentists, and the other group is the Bayesians. The first one, the objective probability, is a part of a relative frequency of occurrences of a specific event. If you run an experiment, if this goes to infinity, then the probability should be the value of how often does this occur with respect to the number of experiments that you performed. So basically, if you have a dice and you throw it infinitely many times, then you will know exactly what the probability of each of the possible events is, namely the numbers of the dice occurring on top. The alternative way of looking at this is to have probability as a certain degree of belief. So you believe you have a dice, and you see it, and it has six sides, and you believe, you assert the assumption that this will end up 6 times on each of the sides on average when you run the dice. So it's a different way. This is an idealized rational individual. It's a different way of thinking about the same concepts and similar mathematics, but it's interesting to be aware of that. So frequentism is really just the probability as an outcome of some repeated experiments, and that's different to the Bayesian approach. So if you would ask, if you read in an article that 1 in 5 people is having an affair, and I talk now to one specific person, then I could assign to this specific person that the probability that you're having an affair is 20%. So that's quite high. What do you think about it? Is that something you would like to discuss with us? So this is something that assigns a specific belief to a specific individual in your space. But that's not in principle, in the frequentist understanding, is not the right way of looking at things. So the probability is rather of 20%, is rather, if I pick randomly people out of a random pot of candidates, then the chance that if I do that infinitely often, that I would get 20 of the 100 I get who have an affair. So I can only say something about a specific group and about a specific experiment. Which is different to the Bayesian approach, which is an expression of the uncertainty and the belief explicitly model, where you can assign that. So it's really then about the individual and something saying about this individual. So I simply move on. So now let's try to formalize this, and in principle this applies to the two philosophies. And these should be terms that you have seen before, you're familiar with. So basically you have a sample space, which is a set of possible outcomes of your experiment, part of this experiment. So you could throw a dice, it would have a sample space and head and tail. You throw a coin, head and tail. You throw a dice, you have just a set 1, 2, 3, 4, 5, 6. Or you throw two dice at the same time, and you get the ordered results. And then you have it's an 1, 1, or 1, 2, 2, 1, and so forth. So these are the sets of single outcomes of an experiment. And so each of those events are the things that have probabilities, and these are the things that are a subset of the probability of the sample space. So this is often called the event space. So it's all the possible events, and it's just the power set of the sample space. So we have these are the objects themselves, so the samples themselves. But then we also have an event which could be either 1 or 2 coming out, either 1, 2, or 3, up to any of them. And so if we have a finite sample space, then we usually consider the power set to 2. So now we have the probability theory as a language to deal with these events, and we can assign some value based on our assumptions. So that's a very Bayesian term of looking at things based on the assumptions or based on some previous experiments. We can sort of assign a prior probability to a certain event happening. So we can say that the event that if I throw this dice and I get a 6 is a 1 over 6, because it's the size of the it's the size of the event divided by the size of the sample space. That's one way of defining this probability to this individual event. And there is another example where we have a sort of, from a weather forecast, we have a value assigned to the weather, the variable weather will get a certain value, such as sunny. That's the example that comes from the book again, which we sometimes abbreviate as sunny in this sense. And that corresponds to the belief which we have before we do any experiments or we don't have any more evidence. So that's a prior probability that's assigned to a certain event. And we often have a possibility that a certain variable can take several values. So we have the values sunny, rainy, cloudy, and snow. And then if we take the complete, if that's a complete set, and we take the probability values for the individual events, then we can write down the complete probability distribution for a certain variable. And that should be normalized and sum up to 1, so that we can then apply the mathematical foundation, the mathematical theory of probability theory. And based on the notion of the prior probabilities that we have a notion of a conditional probability. So that is given a certain event A, if we know B, then what is the probability of A happening? And that is simply defined as a P with this bar A under the condition of B as the probability of these two events happening at the same time, normalized by the probability of the event B happening. There's an alternative way that we're going to look into, or that we're going to use later in calculating with this, which is just exactly the same, but written in a different way, which is the product rule. So this is now establishing our language. And basically, I think I can skip this slide. So then the next step is to define a joint probability distribution for a set of random variables, which is then the combination of the two. So we can say if we have a distribution of sunny, rainy, cloudy, and snow for one type, and the cavity being true or false, then I can write down the full combination of all the probabilities for the individual values. So in principle, when I have this joint probability distribution of dependencies of variables of each other, then I can calculate, can in principle answer all the questions about the conditional probabilities about this domain based on this joint probability distribution. So this gives me one way of calculating the values for some conditional probabilities. So if I want to do this, given a certain joint probability distribution, then I can just write down the full distribution over all the variable values, like here. And then I just have for every proposition to sum up the values of this individual table to come to my probability. So if I want to know what the probability, given this joint distribution of toothache is, I just have to look at all the ones in this green field and sum up the probabilities to get to the probability of this specific variable. And if I have a conditional probability, I just look at the, given the formula for the product rule, I just have to look at the individual elements here in the green one, and divide it and normalize it by the full probability of someone having toothache. So this is the sort of standard ways of calculating individual values of your domain based on the given probability distribution in very simple ways. So that was the sort of enumeration, which can be very expensive in calculation. There's an alternative way or an additional way, and that is using more calculus with which you can calculate. And there is an axiomatization of probability theory, the Kolmogorov axioms. And basically, these are then the properties that you have for any event A and B. You can always show, if you have a true probabilistic approach, that the probabilities are between 0 and 1. That's the axiom that has to be fulfilled for probabilities. The second one is that the whole sample space should have 1 probability. The disjunction is defined in this way. So you just add the probability values for the individual ones, and you deduce the conjunction, so that both happens at the same time. Or in this specific case, if two events are independent, you can just add the probabilities. So if you have these axioms, then you can simply do calculation with that. So you can prove, for example, properties that the probability of the empty set is 0. So that's a fact that follows from the Kolmogorov axioms, and you can simply show them by this simple calculation step that we know that the full probability is 1, that the samples, the empty event on the sample space are disjoint. And then you apply the third rule here, which I've, this one, the definition of the disjunction, or the union, and then you get to the definition here that the probability of the empty set must be 0. So that's one example. And this is another one. If A is a subset of B, then the probability of this event A must be smaller than the probability of the superset. And you show this by applying simple set theory and then the Kolmogorov axioms, and then you get the fact that you derived. So I think one of the interesting applications is a very simple one, and that is the application of the Bayesian rule. And this is basically to solve this inversion problem that you often have the probability of a consequence given the cause, but you're in principle more interested in the other way around, that you have a cause and you want to know the reason for it. So we'll see an example in a minute. You have, it's easy to study the probability of some symptoms given some illness, but that's usually what you not need if you have, if you are a doctor, you want to estimate the probability of someone having a specific illness when they have some symptoms. And this is what you can apply this very simple calculus rule for, that has the name given by Bayes. And it's clear that this rule is true, so this is easy to see where this comes from. This also comes from the axioms and the properties of probability. So this is the rule that you can estimate the probability, you can calculate the probability of A given that B is true, simply by calculating the probability of A, multiplying it with the probability now of B being true under the condition that A is true, and normalize it by the probability of B being true. Here is the proof, which is easy to see where this comes from. So this is what we want to prove. So you just apply the definition of the joint probability. You can get rid of the P of A, and then this is the definition of the joint probability the other way around. So it's easy to prove that this is true, but it's still a very powerful and nice rule in these cases where you know or can easily estimate the probability of a certain disease being true. And given that you have a disease, you can also measure, you know how many people have headaches when they have a flu. This is something easy to measure, but the other way around is far more difficult. Similar example is if you want to know whether something is a spam, then it's easier. Then it's easy to identify whether something is spam, and then you can count the words. But what you really want is, if you have the words of your email, for example, that you can estimate what the probability is that something is spam. So that's the power of this rule, and it is also something very often applied, and I think it gives quite interesting results. So I'm not a probability person, as you might have noticed. So to me, this gives a very good intuition of how wrong one's intuition can be, just by applying this calculation. So if you look at this example of medical knowledge, that the experts tell us that a particular tumor has a certain type of probability of being malign, then you do some tests on it, and these test results are as follows. Probability that a malign tumor yields a positive result, so that's the wrong direction, has a certain value, is relatively high. So when you have the tumor, you get the positive result of your treatment, your radiology, and the probability of the negative result for a benign one is 0.9. So you have still a relatively high error rate, but still, it's very clear that 90% of the people who don't have it also get the result rightly from this test. So it seems like a good test. The question is, how high is the probability that if you have the test saying you are positive, it's positive, so you have the condition, you have this tumor, how high is the probability really that you have this tumor? And that's something that you can now nicely calculate with this Bayesian rule. And interesting, so that is not only my intuition, but it's also the intuition of doctors, for example, that they say, okay, if this result comes back from the lab, then these people have probably the tumor. But this is absolutely not the case. If you apply Bayesian rule, then you can use all this information to calculate the real probability. So this is just filling in the values as I named them in the story. And by Bayes' rule, just filling in those values, you can show that the probability is not even 10%. So far lower than what the physicians would think. So this is one of the means of probability. It's a very old one, but I think it's still a very powerful one. And we look into this, the effect of this rule on Monday as a very simple and effective machine learning method. Namely, learning prior probabilities and then the estimation of whether something is in spam or not is a very simple algorithm to show one of the benefits of machine learning. Problems is that you need a lot of data. This is nowadays improved a little bit, but still you need these all the combination of the evidence. In principle, if you have your joint probability distributions, your tables get enormous. So we have similar problems like we have in propositional logic here as well for efficient reasoning. So if you have just 20 symptoms, you already get over 1 million combinations. So that is already becoming prohibitive. And one of the things, yeah. Yeah.
So the last sentence inconsistency.
So that is related to this trick that I'm going to talk about now. So it's so the idea is that in many of the symptoms we know whether they are related or not. So in this joint probability distribution that I showed 50 minutes ago, we had toothache, and then we sort of compared the probability of having toothache and the weather. And there is a high chance that these two events are not related. And if you are sure that two events are not related, then basically you can have independent calculations and combine the values, the input and output of your individual calculations into a network. And that is what these graphical models, probabilistic graphical models, such as Bayesian networks or Markov networks, do. And that is what I think is a very interesting subfield of AI that we do not have much attention here at the FU. I think they do a little bit at the UVA, but also not that much. But it's a very active research field. And the idea is that if you assume this conditional independency, you can build networks where sort of you feed your probabilities into as input to the others, and this strongly reduces the size of your tables that you need to calculate. But it can be very wrong, and it can be almost so wrong that it gives you inconsistent results. So that is yeah. So very brief word on those probabilistic graphical models and the Bayesian networks. This would be an example for it. I will show it in a couple of minutes. It's a very simple graphical notation of this independence assumption. And the way you define that is as a graph where we have sets of nodes, and every variable corresponds to a node or the other way around. Every node in the graph corresponds to a variable, and we have a directed acyclic graph. So that is one of the differences between the other models. So the Markov models are, I believe, not of this nature. This is the simplest version of the Bayesian networks where you have this, and you have a conditional distribution given for each of the nodes that depends on the parents, the information that it gets from the parents. And then the nice thing is, and that what sort of gives the value to these networks, is that the topology can help you in reducing your complexity of the reasoning. So, for example, if we know that the weather is in principle independent on the fact whether you have toothache or not, then we can model them simply as two different networks. While you can then say whether you have a toothache or a catch, I don't even know what a catch is also something that's independent, but both of them depend on the fact whether you have a cavity or not. Then you can model them in this way. So this is the representation of two facts that are conditionally independent, namely toothache and catch, but both depend on the cavity, the fact whether the probability whether you have a cavity or not. And that is an example for it, just to get it the intuitive idea. So you're at work, the neighbor John calls to say my alarm is ringing, but neighbor Mary doesn't call. So sometimes it's set off by minor earthquakes, and the question is there a burglary? So we have the variables burglary, earthquake, alarm, John calls, Mary calls. And then we have some knowledge about it that we have modeled in these probability distributions, and there is the causal relations that you model, the knowledge that you model here, that a burglar can set the alarm off, an earthquake can set the alarm off, the alarm can cause Mary to call, and the alarm can cause John to call. And this is how this is represented in this Bayesian network. So there is a certain probability of a burglary happen, and there's a certain probability that an earthquake is happening, and the authors lived in San Francisco, I think at the time when they wrote the book. So you see that the probability of there being an earthquake was higher than the probability of a burglary, I think. And then we have this probability here, probability distribution here of an alarm going off based on the assumption that B and E is true for facts whether there is a burglary, there is an earthquake. You have this distribution, and this again is then taken as input for the John calls. So if the alarm goes off, the probability of John calling is 90%, and the probability here is again dependent on whether the alarm goes or not. So what this shows is simply as an example of the dependencies of the probabilities of certain events given on some predecessors in the network. And this topology allows you now to have relatively small calculations on your probability distributions that are easy to handle, more easy to handle, because of the topology of the graph. And of course there are, this I think goes back 15 years, is just a very shallow overview of the general ideas. Of course this is an active research field. As I said, in a way it's a shame that we don't have anything to pursue this in our department, but you can't do everything. So the advantage of probabilities is that they really come with a sound mathematical basis. They can be extended to decision making. We've seen that, for example, with the drugs, or we will extend it to learning tomorrow. And there are good tools available. Also, some that makes the computational bad properties more practically to be able to deal with, like the probabilistic graphical models. The big problem is attractability. That's why these graphical models have such an appeal as well. And the question is, where do you get your prior probabilities from? Is again a similar question to the question of where do you get your fuzzy values from? So it's both very useful technology, but it's also very still difficult and complicated technology. So I want to spend the last 5 minutes quickly to talk about the exam, what you should expect from the exam, and what to expect from the final project. So basically, the lectures are a superset of the material that we're going to ask in the exam, and it's clear that you can't understand and can't be asked to reproduce everything that I said, and neither what is in the book, because the book is even a bigger, so the reader that we gave out is even a bigger superset. So I think the best guideline to understand what you could expect from the exam is to look at the questions from the working groups on Friday, so with Dora and Daria. There's also a practice exam, and in principle what you should be familiar with the basic notions of AI as the following ones, namely informed search with breadth first search, depth first search, and depth first iterative deepening. Uninformed search, I've taken the beam search out because I didn't explain it, so I do it now, because otherwise it will stay in the slides. So this one you don't have to take care of. Adversarial search, how does min-max work, how does alphabetic search work? We have looked at logical representations, and that means you should understand propositional logic, semantics of propositional logic, first-order logic, and the way how to propositionalize a first-order formula into a propositional formula. The algorithm to calculate would be DPLL, so the Davis-Putnam procedure, and then to have some basic understanding of uncertainty and vagueness. And that in particular is if you're given a fuzzy interpretation of propositions, how can you calculate the fuzzy interpretation of a complex formula? So that would be mostly on the vagueness side and the uncertainty side. If you are given some information to work with the Bayesian theorem, to make some prediction on conditional probability, to do a little bit of calculation with the probabilities, like I showed some examples here. You will see some of them tomorrow in the work groups. And then next week we look into learning, and there will also be some more learning concepts that you should be aware of. Indicative, we will have about 25%, 20% sort of reproduction, things that I explained here that I try to make sure this is important. We'll have 50% questions where you have to calculate something, and some of them you will have to type the answers in a free field. Some of them you will have to answer in terms of multiple choice or multiple answers. So if we have a question whether something is satisfiable or whether something is entailed, then you might get five formula that are entailed. You have to calculate whether they're entailed or not, and then you have to click the one that is entailed. So you expect for these do questions both written and both multiple choice. And some open questions, also dealing with the ethical questions and the philosophical questions, where you simply have to write short essays. And the final project, I think you are hopefully now starting really to play around with these agents and to also start thinking in terms of research questions. So we have the question is really to understand the intelligent systems methods. And you should describe that in a paper, what these questions are and how you give answers to those questions. So in order to write a scientific paper, what you need is a research question and a hypothesis, and then you have to give the answers to your question in some systematic way. The order of the paper is in principle free to you, but we give you these sort of guidelines. Start always with a title page and an abstract. Then you have an introduction to the problem and to the paper itself. So it's not an introduction to the field, it's an introduction to the paper. What is you're going to show, what is the approach that you take, and what is the solution that you found. So it can be that complete. Then give some background, so that other people can read your paper and understand what you mean by the terms. Then explain the research questions. The most important thing, people need to understand why you wrote the paper and what you really wanted to answer. And then you have to explain how to set up your results, explain the results, get some general findings out of them. Basically, my research question is true or false, or my hypothesis is true or false because of this and this and this. And then you conclude the paper. And take at least 4 bots. Some of them we might have given you, but improve them, and then compare their performance in some way. Either the quality or the runtime or whatever you want. And then you study the results. Some bots might be better than others. Define some hypotheses on them and give us answers to those. And then there is the standard way of writing such a paper. Just look at the description. That is sort of self-contained. So I think that was it. I would appreciate if some people could come and help me run this experiment now. And for the rest, I'll see you next week, where we talk about machine learning and ethical questions, philosophy, and thank you. Have a good weekend after.